Hello and welcome to another educational lecture series supported by the TEAM-NANO European Horizon program. In this lecture series, we focus on the fundamental concepts in electrochemistry. I am Dr. Evangelia Founta and I'm a research fellow at the University of Southampton. In the first part of this lecture series, we focused on the fundamental principles of electrochemistry and applications in energy. Now in part 2, we will move to practical electrochemical methods. So the goal here is to understand how the fundamental concepts are applied in real experiments to study materials, reactions, and electrochemical devices. So electrochemical techniques allow us to investigate a wide range of properties such as reaction kinetics, charge storage mechanisms, mass transport, and electrode stability. These methods are widely used in the study of batteries, supercapacitors, fuel cells, corrosion processes, electrochemical sensors, electronic memory devices, and many more. In the next slides, we will introduce some of the most commonly used electrochemical techniques. We will then explore how the experiments are performed and learn how to interpret the data they produce. Understanding these techniques is essential because they provide the tools that allow us to connect electrochemical theory with real experimental systems. To begin this section, it is useful to look at a classification of the main interfacial electrochemical techniques. The diagram I'm going to shortly present provides an overview of how different electrochemical methods are organized based on how the experiment is performed. So at the highest level, these techniques can be divided into two main categories, and that is static and dynamic techniques. So the first category is static techniques, or in this case we're simply measuring the potential difference between two electrodes, and the main example of this type of measurement is potentiometry. The second category includes dynamic techniques, where current flows in the system. In these methods, we intentionally perturb the system by controlling either the potential or the current, and then observe how the system responds. So one branch of dynamic techniques involves controlled potential experiments, where we apply a defined potential to the working electrode and then measure the resulting current. Many important electrochemical methods fall into this category. Within controlled potential techniques, we can further distinguish between fixed potential and variable potential methods. So for example, when the potential is varied over time, we enter the family of voltammetric techniques. These include widely used methods such as linear strip voltammetry and cyclic voltammetry, which are fundamental tools for studying electrochemical reactions and energy storage materials. These voltammetric techniques can also be performed under different mass transport conditions. So for example, experiments can be conducted in quiescent solutions where the electrolyte is still, or in stirred solutions, which enhances mass transport. Stirred systems are often used in hydrodynamic voltammetry and stripping voltammetry. If instead a fixed potential is applied, we can perform techniques such as amperometry, where the current is monitored over time at a constant potential. Another example at a fixed potential is controlled potential coulometry, where the total charge passed during a reaction is measured. Another branch of dynamic methods involves controlled current techniques, where the current is fixed and the potential response is measured. An example here is controlled current coulometry, which is often used for quantitative electrochemical analysis. Finally, another important technique shown in the diagram is electrochemical impedance spectroscopy, which probes the response of an electrochemical system to small alternating signals and is widely used to study interfaces, reaction kinetics, and charge transport. It is from this diagram that there is a large family of electrochemical techniques available to study interfacial processes. Here, we will focus on some of the most commonly used ones in practical electrochemical research, including linear strip voltammetry, cyclic voltammetry, chronoamperometry, chronopotentiometry, and electrochemical impedance spectroscopy. One of the most widely used electrochemical techniques is linear sweep voltammetry, often abbreviated as LSV. In this method, we apply a linearly changing potential to the working electrode, meaning that the potential increases or decreases at a constant rate over time. This changing potential is called the potential ramp. And while the potential is being swept, we continuously measure the current response of the system. The resulting data is typically presented as a current versus potential plot, which provides information about the electrochemical reactions occurring at the electrode surface. There are several important experimental parameters that define a linear sweep voltammetry experiment. So the first is the starting potential, which is the initial potential where the experiment begins. This is usually chosen so that no electrochemical reaction occurs yet. And the second is the end potential, which is the final value of the sweep. This is typically selected to ensure that the electrochemical reaction of interest fully occurs. Another important parameter is the scan rate, which describes how fast the potential is changed over time, and thus it is usually expressed in volts per second. The scan rate is important because it is influencing how quickly the system is perturbed and can affect both the peak current and the shape of the voltammetric response. To understand what happens during an LSV experiment, let's consider an example involving a redox active species in solution, such as ferrocene. At the beginning of the sweep, the potential is not sufficient to drive the redox reaction, so almost no current flows. As the potential approaches the redox potential of the species, electron transfer becomes thermodynamically favorable. For example, ferrocene can undergo oxidation at the working electrode to form the ferrocenium ion. As this reaction begins, the current increases because more molecules are reacting at the electrode surface. However, as the reaction continues, the concentration of the reactant near the electrode decreases, and the system becomes limited by diffusion, meaning that new molecules must now travel from the bulk of the solution towards the electrode surface, and this leads to the formation of a diffusion layer. Eventually, the current reaches a maximum value, which is related to the rate at which molecules can be transported to the electrode surface. Moving on, again, one of the most widely used electrochemical techniques is cyclic voltammetry. It is a powerful method for studying redox reactions, reaction kinetics, and charge storage mechanisms. In cyclic voltammetry, the potential applied to the working electrode is swept linearly between two values called the initial potential and the switching potential. Once the switching potential is reached, the direction of the potential sweep is reversed, and the potential is scanned back towards the starting value. Because the potential moves forward and then backward, the measurement forms a complete cycle. While this potential sweep is occurring, the current response of the system is continuously recorded. The result is a plot of current versus potential, which provides valuable information about the electrochemical processes occurring at the electrode. The diagram here shows the triangular waveform of the applied potential as a function of time. As the potential increases, it eventually reaches a value where a redox reaction becomes thermodynamically favorable. Now let's consider a simple redox couple represented here as A plus an electron gives A an ion. As the potential approaches the reduction potential, electrons begin to transfer from the electrode to the species in solution and the current increases. This produces the cathodic peak, which corresponds to the reduction reaction. When the potential sweep reaches the switching point and begins to move back in the opposite direction, the previously formed reduced species near the electrode can now be oxidized back to its original form. This produces the anodic peak corresponding to oxidation. These two peaks, the cathodic peak for reduction and the anodic peak for oxidation, are characteristic features of cyclic voltammograms and form this so-called duck shape. The exact appearance of the peaks provides important information about the system. For example, the position of the peaks relates to the redox potential, while the shape and size of the peaks provide insight into reaction kinetics and diffusion processes. It is finally also worth noting that different conventions exist for displaying cyclic voltammograms. For example, in the US convention, reduction currents are plotted upward and oxidation downward, while the EUPAC convention uses the opposite orientation. But regardless of the plotting convention, the underlying electrochemical processes always remain the same. Now, to better understand cyclic voltammetry, it is useful to examine what happens to the concentration of electroactive species near the electrode surface during the potential sweep. We briefly mentioned it, but now let's see it in more depth. Here we link two important pieces of information. So the cyclic voltammogram here, shown at the bottom left corner, and the concentration profiles of reactants and products as a function of distance from the electrode, shown here in the surrounding graphs. So let's follow the process step by step. So we start at point A, where the potential is still far from the redox potential. At this stage, no electrochemical reaction is occurring, so the concentration of the species in solution is uniform throughout the solution, including near the electrode. As the potential begins to move toward the redox potential, we reach point B. Now the reaction begins to occur at the electrode surface. For example, if we consider a ferrocene system, ferrocene ion can be reduced to ferrocene. As molecules react at the electrode, the concentration of the reactant near the electrode decreases, creating a concentration gradient between the electrode surface and the bulk solution. As the potential continues to increase, we reach point C, where the current reaches the cathodic peak. At this stage, the reaction rate is very high and the concentration of reactant at the electrode surface approaches nearly zero. The current now becomes limited by diffusion, meaning that the rate of the reaction is controlled by how fast molecules can travel from the bulk of the solution to the electrode. After the peak, as the potential continues to change toward point D, the current begins to decrease. Even though the potential is still favorable for the reaction, the reactant concentration near the electrode has been depleted, so fewer molecules are available to react now. After the switching potential, the direction of the potential sweep is reversed. This is where the second half of the cycle begins. Now we move toward points E and F, where the previously formed product near the electrode can undergo the reverse reaction. For example, the reduced species can now be oxidized back to its original form. This produces the anodic peak in the voltammogram. Again, the current initially increases as the reaction proceeds and then decreases as the concentration profile evolves. Finally, we return to point G, where the system approaches its starting conditions as the concentration gradients begin to relax through diffusion back toward the bulk equilibrium. The key idea illustrated by this is that the shape of the cyclic voltammogram is strongly governed by diffusion and concentration gradients near the electrode surface. Now, after recording a cyclic voltammogram, the next step is post-analysis in order to extract useful information from the curve. A cyclic voltammogram contains several key parameters that help us understand the electrochemical behavior of the system, including parameters like charge transfer, reaction reversibility, and the number of electrons involved in the reaction. So the first parameter we can determine is the total charge, denoted as Q. So the total charge passed during the reaction is calculated by integrating the current over time. Since the current represents the flow of charge per unit time, integrating the current allows us to determine the total amount of charge involved in the electrochemical process. This can provide information about the amount of electroactive species or the stored charge in energy storage materials. Another important parameter is the anodic peak current, denoted as IPA. This is the maximum current observed during the oxidation peak, which occurs at the anodic peak potential labeled EPA. So the peak current is typically determined relative to a baseline taken from the zero current region of the voltammogram. Similarly, we can measure the cathodic peak current, denoted as IPC, which corresponds to the reduction reaction. This occurs at the cathodic peak potential, labeled EPC. Again, this value is determined relative to the baseline of the reverse scan. Another useful parameter is the half-wave potential. For reversible or quasi-reversible redox systems, this value can be approximated as the average of the anodic and cathodic peak potentials. The half-wave potential provides a good estimate of the formal redox potential of the electrochemical couple. By analyzing these values, we can also evaluate the reversibility of the electrochemical reaction. Reactions are generally classified into three categories: fully reversible, quasi-reversible, or irreversible. So for a fully reversible reaction, certain relationships are expected. For example, the ratio of the anodic and cathodic peak currents should be close to 1, meaning IPA divided by IPC is approximately equal to 1. Additionally, the difference between the anodic and cathodic peak potentials should follow a predictable value of approximately 0.059 divided by n volts, where n is the number of electrons transferred in the reaction. In addition to identifying peak positions and reversibility, cyclic voltammetry also allows us to extract quantitative information about mass transport and diffusion. One of the most important relationships used for this purpose is the Randles-Shevchik equation. For a reversible electrochemical reaction, the peak current observed in a cyclic voltammogram is described by the Randles-Shevchik equation shown here. This equation relates the peak current IP to the number of electrons transferred, the electrode area, the concentration of the electroactive species, the diffusion coefficient, and the scan rate. One of the most important aspects of this equation is that the peak current is proportional to the square root of the scan rate for diffusion-controlled reactions. Based on this relationship, if we measure cyclic voltammograms at different scan rates and then plot the peak current versus the square root of the scan rate, we should obtain a straight line for diffusion-controlled reversible reactions as shown in the plot, both for the oxidation and the reduction scans. The linear relationship between peak current and the square root of the scan rate confirms that the electrochemical process is controlled by diffusion rather than by surface processes. Using the slope of this line, we can even estimate parameters like the diffusion coefficient of the electroactive species, which is very useful in electrochemical research. Now, as an example, we see a cyclic voltammogram recorded at different scan rates. As the scan rate increases, the peak current increases as well. The scan rate, written as dV to dt, represents the speed at which the electrode potential is swept during the experiment. It has a very strong influence on the voltammogram, affecting the peak current, peak separation, and the relative contributions of Faraday and capacitive processes, which will be analyzed in the next slides further. For example, at slow scan rates, we see that the system has more time to reach equilibrium and diffusion layers develop more fully. At faster scan rates, the system is perturbed more rapidly, manifesting with kinetic limitations or capacitive behavior. Now that we understand how to analyze cyclic voltammetry data, we can use these techniques to investigate how electrochemical systems store charge. Broadly speaking, charge storage mechanisms can be divided into two main categories: capacitive processes and Faraday processes. Capacitive charge storage occurs through physical charge separation at an interface. When a potential is applied, ions rearrange near the electrode surface, forming the electrochemical double layer. In this process, there are no redox reactions and no mass transfer occurs toward the interface. Instead, the energy is stored electrostatically, like in the case of a conventional capacitor. In the case that there is mass transfer to the interface but no redox reactions take place, there is the case of capacitive, non-diffusion limited charge storage. For example, this behavior is seen in electrochemical double-layer capacitors, which are a class of supercapacitor devices. On the other hand, Faraday charge storage occurs through electron charge transfer at the electrode-electrolyte interface. Faraday processes can be further divided into two main categories. The first is diffusion-limited Faraday storage, where the system is often limited by diffusion, which can slow down the reaction at high charge or discharge rates. The second case is non-diffusion limited Faraday storage, often referred to as pseudocapacitive charge storage. In pseudocapacitive charge storage, the system is not limited by diffusion, and as such, it can exhibit behavior similar to capacitors with fast kinetics and high power capability, while still involving Faraday charge transfer though. The underlying phenomena happening at the interface will be explained in the next slide. This classification helps us understand the different ways electrochemical materials store energy. In practice, many real materials show a combination of capacitive and Faraday contributions, and techniques like cyclic voltammetry are often used to distinguish between these mechanisms. We will see some examples later. It is important to highlight that understanding these mechanisms is essential to design improved energy storage systems. So as described in the previous slide, we have three types of charge storage mechanisms, which is capacitive, and then Faraday charge storage, which can be classified into diffusion limited and non-diffusion limited. The two types of Faraday charge storage can be distinguished by the relationship between the rate of diffusion and the rate of the redox reaction. So for a Faraday diffusion limited system, the rate of diffusion is less than the electrochemical reaction rate, so that makes diffusion the rate limiting step. Contrary, for a Faraday non-diffusion limited, else called pseudocapacitive system, the rate of diffusion is bigger than the rate of the electrochemical reaction. And then the electrochemical reaction is essentially the rate limiting step. Essentially, a pseudocapacitive charge storage happens when mass transport of the electroactive component on the surface of the electrode is faster than the rate of the electrochemical redox reaction. Many systems, however, as we said, practically work under mixed regimes where both phenomena affect the total current density. So charge storage mechanisms can be quantified via various methods. One of these is the DAN method, where the total current can be deconvoluted to the relative contributions of each charge storage mechanism. This can be achieved by acquiring cyclic voltammetry or linear sweep voltammetry curves at various scan rates. So the total current is essentially the sum of both Faraday diffusion limited and pseudocapacitive non-diffusion limited plus capacitive proportions as described by equation A. This is based on the fact that Faraday diffusion limited current scales with the square root of the scan rate, whereas the pseudocapacitive non-diffusion limited current scales linearly with the scan rate. By plotting the current divided by the square root of the scan rate versus the square root of the scan rate, a curve is acquired, and by applying a linear fit, as we saw in the previous slide with the Randle-Sevcik plot, the slope k1 and intercept k2 can be calculated, and consequently the relative current proportions at a specific potential. It should be noted that each current/potential point in the CV curve is characterized by a separate set of k1 and k2 values. As a result, by performing the analysis at several potential points, we can get the cumulative contributions to the total current. So now the pseudocapacitive, which is the sum essentially of pseudocapacitive non-diffusion limited current plus the true capacitive, needs to be further deconvoluted as it contains both pseudocapacitive and true capacitive charge storage contributions. So true capacitive current originates from the electrical double layer charging, characterized by a double layer capacitance CDL. Thus, for the calculation of CDL, which is constant in the system, a potential window delta E is chosen on the CV of interest. Within that window, no Faraday reactions should occur, and as a result, the current would be proportional to the scan rate. For CDL calculation, the double layer capacity delta QL at this point window is calculated first by integrating the current over time based on equation B. Then the double layer capacity delta QDL over the whole scan, anodic, cathodic or total, can be determined by equation C. Finally, the supercapacitive charge can be estimated since the other two terms are known in the last Q capacitive equals Q pseudo plus QDL equation here. So a practical example is shown below, where variable rate CV is performed from scan rates ranging from 0.2 to 0.8 millivolts per second. So after applying the above mentioned done analysis, the charge storage contributions to the total current can be calculated. In the next graph, the deconvoluted current is shown. So an intermediate rate of 0.6 millivolts per second is chosen to show the deconvoluted plot. The relative contributions can be also visualized for its scan rate in the form of a bar chart to monitor the interplay of different phenomena at each scan rate. This analysis overall provides valuable insights in the underlying phenomena in electrochemical systems. Now, another electrochemical technique used to study interfacial processes is electrochemical impedance spectroscopy, commonly known as EIS. Unlike techniques such as cyclic voltammetry that apply relatively large perturbations, EIS studies a system that is close to equilibrium by applying a very small sinusoidal excitation signal. This excitation can be either an AC voltage or an AC current, and it is applied across a broad range of frequencies. The purpose of this small perturbation is to observe how the electrochemical system responds without significantly disturbing its equilibrium state. So let's say that we apply a sinusoidal potential signal to the electrode. This can be expressed mathematically as a function of time based on this equation, where E0 is the amplitude of the signal and omega represents the angular frequency. The system then responds with a current signal that also has a sinusoidal shape at the same frequency, but reportedly it is shifted in phase relative to the applied potential. This phase shift is illustrated here, and we see that the potential oscillates sinusoidally over time, while the current follows a similar waveform, but with a time delay or phase difference denoted by the angle phi. The response current can therefore be written based on this equation here, where phi represents the phase shift between the applied voltage and the resulting current. This phase shift arises because electrochemical systems behave as a combination of resistive, capacitive, and diffusion controlled elements. Each of these elements responds differently to an oscillating signal. To describe this behavior mathematically, the total impedance of the system is represented as a complex number, and as shown on the equation here, this expression, impedance can be written based on that. In this expression, the impedance contains both a real component associated with resistive processes and an imaginary component which reflects capacitive or diffusion related effects. By measuring the impedance over a wide range of frequencies, EIS allows us to separate different electrochemical processes that occur at different time scales. So, for example, high frequency measurements often probe solution resistance, while lower frequencies can reveal processes such as charge transfer reactions, ion diffusion, or mass transport limitations. Now, once impedance data has been collected using electrochemical impedance spectroscopy, the next step is to visualize and interpret the results. So, two of the most common ways to represent impedance data are the Nyquist and Bode plots. As we discussed earlier, impedance is a complex quantity, meaning it has both a real and an imaginary component. So these components represent different physical processes occurring at the electrochemical system. So in a Nyquist plot, the real part of the impedance is plotted on the x-axis, while the imaginary part of the impedance is plotted on the y-axis. Each point on the curve corresponds to a different frequency of the applied AC signal. So the x-intercept at the high frequency region corresponds to the ohmic resistance. At high frequencies, the system response is dominated by resistive effects such as the electrolyte resistance. As the frequency decreases, the semicircle appears due to the interaction between charge transfer resistance and double layer capacitance. The diameter of the semicircle represents the charge transfer resistance, which is associated with the kinetics of the electrochemical reaction occurring at the electrode surface. At even lower frequencies, mass transport effects become dominant. So in this region, diffusion processes dominate, as you see in this example here. In this region, often a 45-degree tail appears, which is known as the Warburg impedance. To model all of these, electrochemical systems are often represented using equivalent electrical circuits, such as the randless circuit shown here. So this model includes the solution resistance Ru, the double air capacitance CDL, the charge transfer resistance RCT, and the diffusion-related Warburg element ZW. Another way to visualize impedance data is, of course, the Bode plot. So in a Bode plot, the frequency is plotted on a logarithmic scale on the x-axis, while the magnitude of the impedance and the phase angle are plotted on the y-axis. This representation makes it easier to observe how different processes dominate at different frequency ranges. So for example, resistive behavior typically produces a phase angle near 0 degrees, while capacitive behavior produces a phase shift approaching 90 degrees. Together, Nyquist and Bode plots provide complementary ways to interpret impedance data and help identify the electrochemical processes that control the system's behavior. Now, another widely used electrochemical technique is chronoamperometry. So in this method, the potential of the working electrode is stepped from an initial value where little to no reaction occurs to a new value where an electrochemical reaction becomes favorable. Once this potential step is applied, we record the current as a function of time. So right after the step, there is a current spike that corresponds mainly to the capacitive charging of the electrochemical double layer at the electrode surface. Essentially, the electrode surface charges almost immediately, giving a short-lived capacitive contribution. At the same time, if the new potential drives a redox reaction, a Faraday current also begins to flow. However, as the reaction proceeds, the electroactive species near the electrode surface becomes depleted. Since the reactants must now diffuse from the bulk solution toward the electrode, the reaction rate becomes diffusion controlled, leading to the characteristic decay of current over time. This time-dependent decay is described by the Cottrell equation, which essentially tells us that the current is inversely proportional to the square root of time, which reflects the growing diffusion layer as the experiment progresses. And because of these relations, chronoamperometry tells us how an electrochemical system responds over time after a potential step, and it is especially valuable for understanding the interplay between electron transfer and mass transport. We now move to one of the most important practical applications of that concept in energy storage, and that is cycling, also called galvanostatic charge-discharge testing. So in this technique, we apply a constant current to charge and discharge an energy storage device, such as a battery or a supercapacitor, while continuously recording the voltage as a function of time. In practice, this is usually done using a battery cycler like the one shown on the left, which can test many cells simultaneously under well-controlled conditions. One key parameter that we can get from this test is capacity. Another important term that we see here is the C rate, as shown here. So the C rate tells us how fast the battery is charged or discharged relative to its nominal capacity. A 1C rate means the full theoretical capacity is reached in 1 hour. A 0.5 rate would take 2 hours, while a 2C rate would take only half an hour. This is important because battery performance often depends strongly on rate. At low C rates, the battery has more time to complete ion transport and redox reactions, so it usually delivers higher capacity. At higher C rates, polarization and mass transport limitations become more important, and the accessible capacity often decreases. This is exactly what the graph on the right illustrates. It shows charge-discharge curves recorded at different C rates, from 0.1C up to 2C. At the lower rates, the curves show higher relative capacity, while at higher rates, the available capacity becomes smaller because the cell is being driven faster. From cycling data, we can also evaluate energy density, power density, and cycling stability. Energy density reflects how much energy the device stores, while power density describes how quickly that energy can be delivered. Cycling stability refers to how well the battery retains its capacity over many repeated charge and discharge cycles. So in summary, galvanostatic cycling is one of the most practical and informative techniques in battery research because it links electrochemical behavior directly to real device performance. After discussing electrochemical methods and performance evaluation, it is also important to take a step back and ask ourselves, what are the current challenges in energy storage? As this slide suggests, the future of devices in a holistic way is expected to be soft, smart, and sustainable. Among these, I want to focus especially on the idea of soft energy storage. By soft, we mean flexible, we mean lightweight and mechanically compliant energy storage devices that can be bent, twist, stretch, or conform to curved surfaces without losing functionality. This is important because many emerging technologies are no longer rigid. Modern electronics are increasingly being integrated into wearable devices, electronic textiles, skin-mounted sensors, soft robotics, and biomedical systems. In these applications, a conventional rigid battery can become the limiting component, even if the rest of the device is flexible. So the goal is not only to store energy, but to do so in a form that is mechanically compatible with the final application. A flexible battery can follow body movement, integrate into fabrics, and improve comfort, safety, and design freedom. However, this comes with major challenges. One challenge is that traditional battery materials are often brittle or rigid. A second challenge is maintaining electrochemical performance under mechanical stress. And another challenge is the trade-off between flexibility and energy density. So this approach here brings together two important challenges in modern energy storage: electronic waste and the need for flexible, sustainable battery materials. There is a known growing problem of battery-containing electronic waste, otherwise known as e-waste. As portable electronics continue to expand, more devices reach the end of their life, creating large amounts of waste and increasing pressure on raw materials and disposal systems. One promising direction to replace part of the conventional battery components with renewable and more sustainable materials is proposed. Here the focus is on nanocellulose, which originates from cellulose, the main structural component of plants and trees, with the same natural polymer that is used to make paper. So what makes nanocellulose especially interesting is that it is lightweight, flexible, abundant, and bio-based. When combined with graphite, which is an electrochemically active and conductive battery material, it can form a composite electrode that is not only functional but also mechanically flexible. The images on the right side show that these nanocellulose graphite electrodes can be fabricated as thin, freestanding films that can be bent and twisted without breaking. This is very important for applications in flexible electronics and wearable devices, where the electrode must maintain performance even under deformation. And finally, the SEM image above gives us a closer look at the internal structure of the material. We can see graphite particles embedded within a nanocellulose fiber network, and importantly, we can also observe porosity in the structure. So after discussing batteries, it is useful to introduce another important class of energy storage devices, and that is supercapacitors. So supercapacitors, also called electrochemical capacitors, are devices that store energy mainly through charge separation at the electrode-electrolyte interface, but it's not always limited to that. They are excellent for delivering or accepting energy very quickly, so high power, while batteries are better for storing larger amounts of energy over longer times, so higher energy, which is also clearly shown in the Ragon plot where specific energy and power are correlated. And because of this difference, the two technologies are used in different applications. Batteries are preferred when long-duration energy supply is needed, such as phones, laptops, or electric vehicles, and supercapacitors are preferred when rapid charge and discharge, high power delivery, and long cycle life are critical, for example, power buffering or backup power. A class of supercapacitors are electric double-layer capacitors, or EDLCs. In EDLCs, ions from the electrolyte accumulate on the surface of porous electrodes when a voltage is applied, forming an electrochemical double layer. Structurally, two porous electrodes are divided by a separator and the space is filled with electrolyte. And when a voltage is applied, positive ions move toward the negative electrode and negative ions move toward the positive electrode. These ions accumulate at the surface of the porous electrode material, forming the double layer, so energy is stored electrostatically, not through bulk chemical change. So a major advantage of EDLCs is that the process is highly reversible, which gives supercapacitors very long cycle life, often much longer than batteries. The most common electrode material for EDLCs is activated carbon. So activated carbon is widely used because it has very high surface area, often due to its highly porous structure. And since charge storage in EDLCs occurs at the surface, a larger accessible surface area means more charge can be stored. There are also other types of supercapacitors based on different operation mechanisms, including pseudocapacitors, which are based on Faraday reactions occurring at or near the electrode surface. So unlike EDLCs, they do involve electron transfer. Typical materials include transitional metal oxides, such as manganese oxide or ruthenium oxide, and conducting polymers. Hybrid supercapacitors are another class, and they combine features of both batteries and supercapacitors. Usually one electrode behaves more capacitive, while the other behaves more battery-like or pseudocapacitive, or we can have mixed mechanisms in the same electrode. The goal is to balance high power with improved energy density, and an example is lithium-ion capacitors. So thank you very much for following this lecture series supported by TEAM-NANO European Horizon program. I hope you had the chance to learn some new concepts which will be useful in your future studies and your research.